So last time we started to talk about the internal force. I said if we go ahead and cut a member to the half to see what happened inside that. I said okay, there are going to be three forces: normal force that's going to either pushing it or pulling it apart. There's the shear force, which basically wants to cut it, and the bending moment, which wants to bend it. There's a convention sign for that, so to which they want to. But when we want to work with them, we want to find out, okay, when we say it's a positive normal force, what does it mean? And whether it's a negative normal force, what does it mean? So if I have, this is a very conventional form of working that. So if I have two parts of my, like this, these are the positive ones. If they are look like this, they are very positive. So for the N, it's like that. Positive is if it's the other way, it's negative. For the V, it's positive. It's like this on this side and this on this side. Otherwise, it would be negative. And for the M, this is positive.
On the blue marker, what letter goes with that? Is that
V? That's a V.
Okay, that's what
So this is considered to be positive, positive internal forces. If it looks like that, or positive. If it are opposite of that, it would be considered as a negative. So let's look at an example. Have a beam like this. Let's start with a simple example, and then we'll go on. Or it's the other way. And it's going to be 6 Newton line somewhere here. Three and 6. That's going to be A and D. So, if this is the case, if this is the beam we have, assume we want to know how much is the shear, the internal force right before that point here, and right after that point here. So it's a point C and point. I want to know wherever is that force, the 6 kilonewton force. I want to know how much is the internal force at the C, and how much will be exactly right after that at D. So the first step is that to do that, first I have to go ahead and find the reaction of the support. So the reaction of support here I have for the A is going to be just AY. Here I have DY. And let's see which way. And dx. And also there's a non-termination there also here. So the first step is that to find the reaction of the support. If I go ahead and consider the entire thing, so for AD, so I consider the entire section, and then I will write the equilibrium equation there to find. So sigma fx0, what will you say? Dx 0, because I don't have any force in the x direction, right? Then sigma fy0, I will end up with two unknown if I write the sigma fy0. It's going to be ay and dy. So I have to write the moment about one of the points. So, for example, if I write it about point D, if I write sigma and about D 0, assume counterclockwise positive. So I have ay times 9, and it's going to be clockwise, so it's going to be negative. Then I have 6 kilonewton times 6, and it's going to be counterclockwise, so it's going to be positive. And then I have that 9,000 there. It's counterclockwise, so it's going to be positive. Right? So if I solve that, I should get the AY if I had it, correct? So AY should come out at 5,000 years. And then I can write the sigma if y is 0. And if I write the sigma if y is 0, it's going to be AY plus dy minus 6,000 to be 0. Therefore, the AY would be sorry, dy would be 1,000. If I go over here. Should be right here. That's it. 6,000 down, 5,000 up here, so this should be 1,000. So this is a reaction of the support. The next step is that I want to see what happened at C. So I will go ahead and I will cut that at C. So I will say for AC. If I cut it, if I go ahead and cut that at C, this is what I'm going to get. So it's going to be this is the point A, and this is the point C. What I have there is that it's the AY, which is 5,000. And then any other external forces. So if I cut it there, that's the only external forces I'm gonna have. And then look at I cut it here. This is the left part. So I have to put them like this, because this is this half I'm looking at. So I'm gonna have these three there. So I'm gonna have V going down, N like that, and M like that. So these are at C. So if I go ahead and write the sigma fx0, it gives me the NC is equal to 0. So basically, my section is not in tensional compression. Then if I write the sigma y fy is 0, gives me the BC is 5,000. Right? And if I write the sigma m about point C is 0, then I have 5,000 times 3 plus MC is 0, so the M at C would be 15,000 electron meter. Any question up here? Now I want to see at the D. It's just a very tiny after that force. It's going to be for AD. We already used this one. Let's use another. ABE. Let's put it E. Or AE. What happened to B?
Oh, I think C is supposed to, in the drawing, at least that's B. Okay, but we don't need to be.
Somehow we skip B. So I'm going to draw the AE. So if I draw the AE part, so it's going to be here. And then the external forces I have is that the same 5,000 going there. And this time I have the 6,000 going down. In the previous one, the 6,000 was not there. Now the 6,000 is there. And then again, because I'm considering that half, I follow that convention. So it's going to be N at E, I would say, B at E, and M at point E. It's similar for that one, the sigma of X again. 0, the N, E, 0. Sigma of Y is 0. This time I have 5,000 minus 6,000 plus minus BE is 0. Therefore, the BE would be negative 1,000. And then I would write the sigma m about E 0. Again, if I write the sigma m, it's going to be 5,000 times 3 negative, and everything else doesn't have the moment, plus ME would be 0, then M at E would be 15,000 Newton. Any question? So as you can see, one way I could have done that, I could have considered the other half instead of dealing, for example, for that section, instead of having the AC, I could have the DC and write the same equation for that. Or instead of having the AE, I could have DE and write the same equation for that. So you can look at it, whatever half is the right half or left half, whichever is the easiest, just choose that. Next example, as we have, let's see. Okay, so I have a beam like that, and there's the external force, one on that. And A, C, A, one point five meters. So I want to find out how much is the internal force at point C. This is the point C. If I cut that in half at point C, I want to see how much. So this example has two good points. One of them is that how we deal with the distributed load, and the other one how we are dealing with the supports. So remember, I always said when you want to start it, go ahead and find the reaction of the support. So consider the entire body and find the reaction of support. This is one of the examples that actually you don't need to do that. I will show you why. The other point was that remember I said when we are calculating the internal force, if there is a distributed load, do not touch the distributed load until you cut it in half. Okay? If there is a distributed load, do not touch the distributed load until you cut it in half. So I'm not going to replace that distributed load with a single load yet. I will cut it in half first, and then I will do that. So I will cut it in half, and I'm gonna have AC or BC part. And I'm gonna choose the BC part. So if I go ahead and cut it in half, and it's gonna be C, and it's gonna be B. It's gonna be force on that. It's gonna be 1.5 meters. And then it's going to be the internal forces. Because it's the right hand side, so I have to choose the internal forces like that. So it's going this way as N and C. It's going up this time, B at C, and the moment should be like that. Because this is the other half yard. The right hand, so everything should be that sign convention that we had, it should be like that. So, first question, why I did choose the BC rather than AC?
Doesn't have all like the fixed reactions.
So, I do not need to calculate the reaction. If I choose the AC, it gives me the same solution. The only problem is that I have to go and find the reaction of the support at point A. So it just saved me of doing that. The second part is that, okay, you see I didn't cut it, I first cut it and then I put it there. Now I want to know how much is that force. So let's draw the entire thing again. If the load I have is like this, how much is that? 1200. So this one is 1200 Newton per meter. So I have this triangle, and this is 1200. And then I cut it at the C, means that I cut it here. And if I call this X, how much would be the X? So this entire thing is 3. This one is 1.5. There's a, I don't remember what's the, there's a rule in geometry that is that the smaller triangle would be proportional to the bigger one in this case. So here, if this is a for 3, if this is 1200 Newton per meter, if for 3 meter, 1200 Newton, then for 1.5 meter, how much it would be, and then if you calculate, it's going to give you the 600 Newton per meter. So basically, the distance is half, so that's going to be half. So that is going to be 600 Newton per meter. Still, I cannot work with that because it has a distributed load. I have to go and replace that distributed load with a single load. So I have to go ahead and redo that again and say, okay, this is my B, that's the C, that's 1.5, and then I have this X and C. B, C, and C, and then I know that that's going to be passed through the centroid of that triangle, which is 2/3 from this end. So it's going to be, the magnitude is equal to the area. So it's going to be half of 600 times 1.5. Right? And the location is going to be 1/3 from the base. So that distance is 1/3 of 1.5 and 2/3 from the other end. Is it clear up here? So the next is relatively straightforward. Sigma of x0, sigma of y0, sigma of 0. So if I write the sigma of x is 0 for this one, so for EC, if sigma of x is 0 and C would be 0, if the sigma of y is 0, tells me that the BC minus half of 600 times 1.5 would be 0, if I have that. So it should come to 450. So BC would be 450. And then sigma m about C would be 0. And if I write it about that point m, counterclockwise positive, so it's going to be half of 600 times 1.5 times the distance, which is 1/3 of 1.5, and it's going to be negative, let's get clockwise, minus C would be 0, and therefore C would be minus 200, 25 Newton meter. Any question? Next is the shear and moment diagram. remember that I said, assume I have a beam and any beam that I can. So I have a beam. Piece. And there's another beam. That's why I have a beam like this. And there's a force applied. This time, as assume it's going to be the A, B, and there's going to be point C somewhere. C. In the previous section, we learned that how we calculate the moment or the internal force, moment, shear, or normal force at a given point. But usually, later on, we will see that in the strength of material, we want to design that beam. So knowing at one single point is not going to be helpful. We want to know where each of them become max. I want to know where the normal is the max, where the shear is the max, where the moment is the max. So when I design the beam, I design it for that spot. Because if I design it for example, here, and it's, for example, the shear is not maximum there, so it's going to break wherever it's going to be max. To do that, I need to find the shear, the normal, and the moment is the entire beam. So that is called the shear or the moment diagram. So I want to see how it's going to be changed throughout that. The way it works is usually like that. I will go there and I assume the point C, that point C is sitting at distance of x from the beginning of that object. And if this is the entire length is L. And then I will cut it here at that point X, which I don't know where it is, because I just assume it's somewhere there. I cut it into a half. And this is what I'm going to get. And then I have the internal force here. I have the F here. And then I have N, B, and N there at that given point, which I don't know. Then I have this distance here is x, and this distance here is L minus x. So that's going to be the AC, and that's going to be CE sections. Now, if I go ahead and settle for AC, I assume I write it for AC. I will get the sigma fx is 0, and it will gives me n as a function of x. Gives me n as a function of x, some function of x. If I write the sigma Fy is 0, then it will give me the V as some function of x. And if I write the sigma M about point C is 0, it will give me the M as some function of x. And where is going to be the x in this case? The x is going to be between 0 and L, between 0 and L, between 0 and L. X starts between 0 and L. And then I can go ahead and draw these two. If I draw these two, I would get, this is the x, and this is the v equal to f1x. And then this, again, this is going to be the x, and this is going to be the m as f2x, f2. And I will plot them. And if I plot them, these are going to be my shear and moment arc. Just remember, that's one important point is that x is always starts from left end of the beam. Regardless where I am cutting, the origin for x is always here. It doesn't matter where I cut or how many cuts I'm going to do. This is the origin for the x. Okay, x, the 0 for x is always going to be here. Regardless of which end I'm going to choose or how I'm going to work, 0 for x is going to be always there. Any question? By the way, here I'm gonna so I'm gonna have the reaction of the supports also here. So it's gonna be A, X, A, Y, M, and A. Also we're gonna have it there. That's all. So I cut it, I put the x at point C here. But in general, where should I put the points? If I have a beam like this, have a beam like that, and then I have some distributed load here. And then I have one F1 here, F2 here, so that will be here. Where should I cut? As I said, assume it's going to be the point A, B, C, D, E, and F. So there are two rules that you have to follow. So you need a section between any two forces. In other words, you need a section anytime there's a change in force. So anytime I have an external force changed, I need a section. The second one is that you need a section in the middle of distributed. So anytime you have a distributed load, by the middle I don't mean just right in the middle. Somewhere you have to cut the distributed load somewhere in the where you have the distributed loads. So these are the two rules that you have to follow. So assume here I'm going to have the AY, AX, and here I have the EY. This part, we're going to do it a lot in the sense of material. So make sure that you follow that. So I have a distributed load, so I have to cut somewhere. So between A and B, I need to cut because there's a distributed load. So my first cut is going to be somewhere there. So that's going to be my first cut. So first cut would be between A and B. So for AB, I have to cut it. So what I would get is something like this. I have the AX and AY. I have the distributed load. And this is the important one. X is going to start from the A to that point that I cut, wherever it is. And then I will have the N, B, and N. Okay. Now, anytime there is a change. So at the time when I get to the B, there is a change in the external force. There's a force, suddenly it's not there. So I need another cut between B and C. So I have to go there and cut somewhere. Again, it doesn't matter where, but should be between B and C. So for BC, I have to cut it. Again, I start it from the here. AX, AY, and B, M, and so this is the point A. So this is the point A, is the point B. Again, the X will start from here to that section. Now look at between F1 and F2. As soon as I reach the F1, again there is going to be a change in the external force. So I need another section there. I need another section here. So for A, sorry. And this is for, it's going between C and D. B and N, and this is point A, this is point B, this is point C, and X starts from here, from A to that point. So again, it's going to be at the F2, it's going to be section, so it's going to be, I need the cut there between D and E. And also at E is going to be the external force is a change. So I'm going to need another section somewhere here between E and F. There. So I'm going to have there. One thing that I want to mention here is that look at for the AB. For the AB, X is between L1, L2, L3, L4, L5. For the AB, X would be between zero and L1. Is that X is from here to here. Okay. For this one, where's going to be X from? Zero to L2. Or 0 to L1 plus L2. So for this one, X is from here to here.
That makes sense as well.
So it's going to be from L1 plus L2. still x starts from there, but we are only interested in this section. For this one, still x start from here, but we are only interested between C and D. So x is going to be L1, L2, start from L1 plus L2, and then L1 plus L2 plus L3. The same is going to be, that's probably, this is very important that you remember. X is always start from the Z, from the very left end. 0 is there. But we only consider the section we are interested in. So we keep the origin, we don't move the origin, but we only look at that. And the same things here, so I don't have an estimate group, so the same things here, I have to have for the DE also. So for the DE, X is going to be L1 plus L2 plus L3, and then L1 plus L2 plus L3 plus L4. So this section, and for EF, same thing. So again, it's going to be the X we are considering. L1 plus L2 plus L3 plus L4, and then L1 plus L2 plus L3 plus L4 plus L1. So only this section. Then we will do the example next time, but what I did here, we have to do it for each of these. So for this one, we have to write these three equations, find the V, N, and M as a function of X. Then here, again, we do those equations, find V, N, and M as a function of X in this range. And then here, again, find V, N, and M as a function of X in this range. And do it for the entire thing. And then we will know that what happened. Question? So just remember that anytime we have a distributed load, we have to cut through it. Anytime there's a change in the external load, also we have to cut the section or cut through that section.